Let me then give a short introduction of Felipe. And so he is an assistant professor at the University of Central Florida. He is an expert on machine learning, probabilistic methods with physics-based models for optimization and uncertainty quantification. And he has industry experience. He was a senior scientist at GE and working on wind turbine performance and reliability. And so he has lots of experience, practical experience with engineering systems. And he has a PhD in aerospace engineering from the University of Florida, and also from the Federal University of Uberlândia in Brazil. So we are really looking forward to your talk, Felipe, and I'm sure all of the audience is too. So thank you very much for joining. The floor is yours. Thank you.
Okay, great. Well, so first of all, thanks a lot for inviting me to talk about my research. So this is something that I like a lot, and I can speak for hours and hours and hours. But I don't know how you guys like to do this. I have a slide deck prepared. We can stop in between. We can wait until the end to have questions. Up to you. Either way works for me.
Let's do this. So if somebody has a question, they can put a question in the chat, and also can raise a hand here on Zoom. And then Felipe can choose whether he is able to answer immediately or wait until the end of the presentation.
Yeah, either way works. I have 3 monitors here in front of me, so
right.
I'm trying to keep an eye on the chat, on people, and on the slides.
Yeah, I would like this to be interactive. Yeah, absolutely. Yeah.
Okay, great. So we're talking about Prognosis digital twin with this caveat that the models are physics-informed neural nets. And I'll get into details of some of these things. But before we do that, why don't we think about the motivations and the path between problems to the actual benefits of having a Prognosis digital twin. So in industry, like in wind turbines, for example, I guess there's no shortage of problems. One major problem is to keep maintenance and operation costs low throughout the usage of the equipment. To be honest, I guess the challenge becomes the fact that much of these failure modes are not necessarily designed or accounted for during design. If you knew that a failure would happen before the useful life of the equipment, you design against. So you can make the case that physics is not fully understood for some of the failure modes at least. Another challenge that you have is that the data is highly unstructured. It's true that we live in an era where data is becoming more available, but it's not as if you can throw sensors all over the map in the equipment, not only because there's increased cost, but also you have problems with whether or not it pays to have the sensor itself, right? So you have to maintain the sensor. So there's a whole host of problems with using sensors in these machines, even though it's true that these days it's more common. The proposed solution that I have for a problem where physics is not fully understood, partially understood okay, but not fully understood, and then data is unstructured, is this hybrid physics neural nets. The benefit being that once you close the loop and have, again, a model that is predictive, you can optimize maintenance and then with that reduce the cost. So that's the motivation. The figure on the right shows the difference that you see in the field with regards to damage levels for a bearing, for example. And it should give you a sense of how difficult it is to have inspection data. In order for you to do this, you'd have to climb a 200, 150 meter tower, shut off the machine, of course, disassemble this. So it's very labor intensive and costly. So the presentation is going to go like this. We're going to dive into physics-informed neural nets, and this audience here doesn't need much explanation, I think, but I'll at least give my flavor of physics-informed neural nets. Sometimes we wish there were consensus, but I don't think that there's consensus on the definition, so I'll give mine. Hybrid models is the flavor that I use for physics-informed, and I'll show you how that can be used in predictive maintenance, especially through application examples. We'll walk through some, and then I'll wrap up with conclusions. Great. So one thing that we like to think when we do neural nets is the means by which you train a neural net. And that's the backpropagation algorithm. The figure A shows the forward pass. I guess that's very trivial. You start with the inputs, propagate to the model, get the outputs. So that's the forward pass. The backward pass is where you use the chain rule to essentially get the sensitivity of the loss with respect to the different model parameters that you want to tweak. I like these plots because I guess they also illustrate the graph nature of a neural net. So if you look into this, it's a direct graph from the inputs to the outputs. The one thing that I like to think when I see this is there is really no constraints about what should be in each one of those nodes. Most of the time we do the weights times bias, or weights times inputs plus bias, and then you pass through an activation function, and you organize that in multiple layers to do a neural net. But there's really no constraints. As long as you can do forward pass and backward pass, very difficult to think that the backpropagation would differentiate what's inside each one of those nodes. So keep that in mind, because that's going to be important down the road. Now, physics-informed neural nets, especially the revised version that I guess became very popular with the work of the Brown University group. And then I guess today we have a lot more people working on it. But it's not necessarily a new concept. The intent is to solve partial differential equations, ordinary differential equations, partial differential equations. Much like we do with finite element, you can start thinking that the mesh is replaced by collocation points, and then the whichever form you're doing the finite element, I guess, is replaced by minimization of a loss function that you evaluate at the collocation point. So if you've done numerical methods for solving PDEs, and if you've done meshless methods or collocation methods, this is a lot like it. It's essentially what it is, a meshless collocation point.
Yeah. Where
the trial solution for the PDEs is a neural net. So it's very neat to think that you can do this, because back to one slide before, we had the gradient being applied to the loss with respect to the trainable parameters. But since you can do chain rule, you can do chain rule of the output with respect to the inputs, and you can do higher orders and whatnot. So this is how you build these models. If you're doing this version of physics-informed neural nets, should I say. Now you look at the literature, and then you're, I guess for the newcomer, it might be overwhelming. I wrote a survey paper published at the Archives of Computational Methods in Engineering, and it's very surprising that the first few papers that I found, they dated back from late 80s, early 90s. So the idea has been around for a while. I think that the main difference, or a very substantial difference, is hardware was not on par back in the 80s and 90s. GPUs and the clusters of GPUs today, it's just unbelievable what you can do. And also, to some extent, the democratization of machine learning through frameworks like PyTorch and TensorFlow, that contributes a lot as well. But we are here to talk about digital twins and prognosis models. So let me tell you how I see physics-informed neural nets in that context. Back to the problem of unstructured data and incomplete understanding of the physics, right? So just think about this problem here for a second. If you were to monitor, let's say, crack growth on a fuselage panel, let's say, I guess you have several options. One option would be you build a finite element model that gives you these stresses, and then you drive Perry's law to do crack growth integration. So let me do the laser pointer here for a moment. Oops. Okay, great. So Perry's law, the way it is here, is an ordinary differential equation. C and M are material properties that you get out of coupon tests. A is the crack length, N is the cycle count, much like discretized time, right? And then delta K is the stress intensity factor, which is a function of geometry. This parameter F encapsulates geometry. And delta S is the cyclic stresses that you get out of the finite element. A problem that you find is that delta K, and I guess because of delta S, might not be accurate because the geometry in the crack growth discretization is usually not very well refined due to computational costs associated with doing this, for thousands and thousands of cycles. So you start doing approximations so that this model becomes computationally efficient. The other problem with this is the boundary conditions might not be well understood. So in this case, you can argue that it's the internal pressure in the cabin that drives the hoop stresses in the fuselage. That might be true, but then in different parts of the aircraft, that might not be the case. So it becomes very hard to do it. Just from even in a simplistic problem like this, you can find a number of problems, not to mention the data problem. So in terms of data for applications like this, it's pretty fair to say that the inputs are a lot more understood than the outputs. So inputs in this case would be the pressures, let's say the pressure over the flight, the cabin pressure over the flight, which you can do a big fat cycle, right? So you pressurize the cabin up to a point, cruise, and then you depressurize the cabin as you land. So one big cycle for that application. But throughout many years of usage, many flights per day, you accumulate a lot of cycles there. One thing that you would not see as abundant is crack length. So the inputs, as far as the stresses, if if you need to account for temperature, velocities, or things of that nature, you get from the sensors installed in the aircraft. But then crack length, you don't, or you don't always get. You might get an estimate of crack length or measurements of crack length between inspection points, but you don't do inspection very often. You usually do these things every 3 years, every 5 years, every year or so, depending on the location of these critical points. So it becomes hard to do a data-driven model since there's this huge imbalance in the data sets. Prediction is hard because then you want to do prediction not knowing the truth in between, and you want to follow the physics to avoid poor decision making in when to, let's say, bring the aircraft down for inspection or to ground the aircraft for that matter. So those are all problems that were brewing in my mind when I was thinking about these digital twins and neural nets, right? Now, thinking that Perry's law is a ordinary differential equation to model the time-dependent growth of crack, back in the day, I was thinking about using things like LSTM and GRUs and recurrent neural nets like those. And then I look at the architecture of these neural nets, and it's quite unbelievable, right? People are very creative. So you look at these things and all sorts of different neurons connected to one another with multiplications and sums. And so this became very complex to me. The explainability here is, I don't know, it's questionable to say the least, right? But one thing that I learned is, there's really very little limitations on how you can connect these nodes within this cell. Then I went back to the drawing board and I said, I can take a recurrent neural net and design the cell myself to do numerical integration of the ordinary differential equations. So just as an example, this cell here would be an implementation of the Euler integration method. Very simplistic, right? Question becomes how to design this F function here that maps the inputs and the previous state to the increment delta A that you update in every cycle, right? But then it turns out that for the crack growth problem, you could argue that F is already well defined by the physics, right? C delta K to the power of N. And so this is where the idea started, right? If I could do this, then I could do numerical integration using neural nets. And I could use physics models to do that. One thing that I learned is that I wanted to use all the luxury that I have at my disposal when I'm doing machine learning models, right? One of the things that is very important is doing the forward pass and the backward pass so that we do backpropagation. At the root of all, I was very concerned about, and I am very concerned about differentiation of this block here, this F block, right? And this is where auto differentiation can help a lot. So if you look at this chunk of code here, I'm showing the snippet of a TensorFlow implementation for that model. And it's unbelievable how simple it is if you're willing to do object orientation. So the mother class layer here, native from TensorFlow, has all the implementation needed to do auto differentiation, forward and backward pass backpropagation algorithm. So we implement a class that inherits that layer class, and essentially you change the, in TensorFlow nomenclature, that will be the call function, which is the forward pass. So we changed that to be a delta K C to the power of n, and then you add the previous state, and then you spit out the updated state, right? So very simple, just like you saw in the block diagram. And with that cell, you can do RNNs. And in this case here, RNN is also the native TensorFlow implementation. I guess in this case, Keras. If you've been around enough, you know that Keras and TensorFlow, I guess today, we can use both interchangeably, but that was not always the case. So, you know, this couple papers that I refer to here in the slide have a lot more details. You can find links to those papers in my website. If you have questions, please let me know. Now, back to the application in the wind turbine, the motivation that I showed you a while ago. These turbines, they're equipped with sensors that will record on a 10-minute by 10-minute basis bearing temperature and wind speeds. And you can see that there is seasonality in these things. A little, you know, a lot more in the bearing temperature, I guess, a lot easier to see. So you have everything that the bearing saw, or not everything, but at least temperature and wind speed. Wind speed is important because that dictates the aerodynamic loading in the blades that gets essentially passed through the bearings, right? The other thing that you see quite often is borescope inspection, like in the figure on the right. And you could see an assessment of how the raceways are, the rolling elements are, but also grease. And for that matter, grease degrades over time, just like any other thing, I suppose. So grease starts in this particular grease with a reddish wine type of color. And as grease ages, it becomes dark and black. So what's the problem that we found here? So the problem that we found to build a digital twin for these main bearings is that the physics of failure, or at least fatigue, for the bearing is roughly understood, not necessarily agreed upon by the experts, but roughly understood at least. Now, grease degradation is horrible, just not an easy thing to model. Although people recognize that as grease degrades, there is a penalty in the bearing life. So the problem becomes how to account for grease degradation. So what we did was we took this data set that we had. It's a data set for a 1.5 megawatt turbine. We had multi-body simulations performed by the National Renewable Energy Lab that essentially gives a map between the wind speed and the dynamic loads that the bearings, the main bearing endures. So this is the loads part. Then what we can do is pass those loads through the fatigue model and start accumulating fatigue. And we could do this on a pure physics-based approach, even if we want to use the recurrent neural nets to do the numerical integration. So the model would look something like this. You have the inputs being the wind speed and the bearing temperature. A chunk of the wind speed gets estimation, is needed for estimating the bearing loads. The wind speed plus, or sorry, the temperature is needed to estimate the state of the grease. the loads plus the state of the grease dictates the where you should be in the bearing operation curve, and then that gives the bearing damage increment. The problem with this model is that, at least in design, you can use this model, but then you have to make assumptions about grease, and it becomes hard to account for aging of grease. So this is where the hybrid part becomes. So I guess there's two ways that you can see this model as hybrid. The first one is there's this physics-based blocks within the recurrent neural net. So the recurrent neural net is data-driven type of thing, or machine learning based. It's doing the numerical integration, and the blue boxes here are data-driven. Sorry, physics-based. Then the question is, if I could, I would have a first principle model for grease degradation. It's just that that's not an easy task. On top of that, it's very difficult to measure grease damage. It's pretty easy to do borescope inspection, just like I showed you a couple of slides ago. So with those things in mind, we decided to do something like this. So you have a grease damage model that is a pure data-driven multi-layer perceptron embedded within the recurrent neural net cell that already has a lot of these physics-informed nodes. So this chunk by itself would be hybrid. And then on top of that, we take the output. There's two outputs here. There is the bearing damage and then the grease damage that you keep tracking over time. But then we take the grease damage and map that grease damage, which is continuum from 0 to 1, let's say, like a health indicator. You map that into a ranking 1, 2, 3, 4, 5 that the technician would assign as the technician climbs the tower and looks at grease. He or she would just assign a number based on what they are seeing up there. So there's this mix of data-driven and physics-informed nodes in this cell. One caveat that I want to show with these left-hand side plots here is that because you have a technician climbing and making a subjective assessment of the grease, that part of the model is subjected to the variability, the uncertainty that comes from that human going up the tower, right? So sometimes you have this reading that comes back at 1 for quite some time, and then all of a sudden it jumps all the way to 4 and 5. Sometimes you have this zigzag because, you know, a month later, a different technician climbed the tower, and you don't want to have bias, or you don't want to have even more bias by telling the technician what was the previous reading, because then you know that whoever climbed the tower that day is not going to throw the other fellow technician under the bus, right? So you don't want to tell the history of that turbine to the technician, so that's a little more clean data. But we took all this and passed through the neural net, went out to do the back propagation. We used a set of, I believe in this application, I believe it was 20 turbines or something on that neighborhood to train the model. For these turbines, we had 6 months worth of data, input data, and these 6 data points for grease damage, or rank, I should say. And then we adjusted the models and we made predictions on 100 turbines. If we can do that, we can also optimize regreasing intervals, right? So the main idea here is, since now I can track grease damage, I can optimize when I want to re-grease the bearings, take out all the junk and put fresh grease there so that I extend the life of the bearing up to a target, right? So as an illustration, you see the unreliability plots for a wind farm or wind park. If you do three things, one of three things, I should say, you can re-grease very often, like every 3 months, which nobody does. And that would make the wind park super conservative, but expensive, right? Because you have to shut off the turbine, climb, and do all that. So you're losing money. You can wait 18 months, which nobody does either, because that's way too aggressive. Or you can use these digital twin models to optimize the re-greasing intervals on a turbine by turbine basis. And then you pick and choose the intervals. And in this case, the target useful life is 20 years. So you bring the park to that straight line there. So that was an interesting application. We speculate a little about how this would scale up. This, I don't need to read. I guess you guys can read what's written here, but you can see that the numbers would, in my opinion at least, would grow substantially. In our little academic exercise, we never felt much. So every time that we decided to train these models or retrain because we missed something here and there, it would be an overnight simulation work. If you want to do this optimization, I guess you're talking about a few hours because you're testing different scenarios, so fine. But if you want to do this on a large scale where you have not only one model, right? This is just the digital twin for the fatigue model of this main bearing, but you'd have like hundreds, tens to hundreds of models to run. Then I think that the problem would become very, very large, fast. So that was the wind turbine application. Another application we had was in collaboration with a group from NASA. And we were looking at degradation of batteries used for, in NASA's case, power drones. But these lithium-ion batteries would, at least today, they are the best bet as far as powering cars and at some point in time, urban air mobility applications like this. So that data from NASA was painful. So essentially they had cycled 8 batteries a lot until they essentially die. And the cycles varied a lot from random loads like the one you see on the right-hand side to constant discharge cycles and everything in between, right? Now, over time, they developed models that could be used for, well, take a step back, models of computational cost that would be compatible with digital twin applications, except for the fact that the models started drifting, or the battery, one of the two starts drifting, depending on how you look at it. The battery ages and it loses the ability to hold voltage. Therefore, there is a discrepancy that starts growing as the discrepancy between the predictions and the observation that starts growing over time. So we decided to do the same thing, to give it a try for these hybrid models. So we built a model that has, in blue, first principle based models. In green, models that are data driven, and then in yellow, it's data driven models as well. And the difference between the yellow and the blue is that the yellow and the green is that the green is deterministic and the yellow is variational. So you have a variational recurrent neural net as a consequence. And this is done so that you start tracking uncertainty in the data. And eventually you start being able to do battery to battery variability as well. So the paper, I should have updated this. The paper was recently published. The title of the paper is correct. I think that I updated here, but I forgot to update on the other slide. So we published this paper where we passed the same methodology to the NASA data set. And part of the benefit was we were able to forecast the aging of the battery and also put uncertainty bounds on that model, which is very important. I assume that maybe it's not as important if you're thinking about batteries for your cell phone or maybe for your Tesla or something. Maybe, I don't know if the uncertainty bounds are that, I guess they are important, maybe not as critical, but for powering flight, so for powering UAMs and UAVs, it becomes very important because what you want to do is assure safety of flight in the future, right? For a mission that you're just going to start flying, I guess that becomes important. But if you're managing a fleet of assets, the cost associated with those batteries. So just think about these companies that have to operate multi-million-dollar assets like the UAMs will be in the future, right? So this becomes very important because it impacts not only safety, but also the bottom line of the companies. So pretty interesting work with the uncertainty quantification portion. We've done other applications as well. This one application here goes back to the fatigue problem, except that here we took a step further and had a problem where the failure mode itself was only partially understood. It's not as if the loads were partially understood. Here, the failure mode itself was partially understood. So we proposed ways to adjust that model form uncertainty, much like we did for the crack growth problem. There's a paper published already, and I guess it's always nice when everything works. It takes a while though to get here, but I guess once you read the paper, you have that warm, fuzzy feeling that this thing works, right? We had a collaboration with NVIDIA back when they were releasing their SimNet toolkit. So NVIDIA has put together a numerical solver of PDEs, right? So much like in the Brown's University flavor of physics-informed neural nets, they developed a wrapper around TensorFlow for physics-informed neural nets. Back in the day, they call it SimNet. So if you Google, you'll find references to SimNet. I think that since late last year or early this year, I can't remember, they rebranded. Now it's called Modulus. So we did a little integration between those two, and I thought it was very interesting because the stresses are a lot better estimated this way, except that here you you still have far field stress theory to do crack growth. So the geometry of the crack is still affected, or not necessarily accurate, as I should say. Then we use the correction factor for that geometry portion of the equation. But the idea of building hybrid models is not necessarily useful only for ordinary differential equations. Last year, we also published a paper where we looked at data coming out of a rig that was testing a torsional vibration damper, a TVD, torsional vibration damper. So it turns out that the viscoelastic material that is used in this application, it's like a rubber, right? Is tested coupons, right, under no stress. So you get the material properties under one condition, but then you pre-stress this and stuff this inside the engine. So the conditions are different, and there's a shift in material properties because of that, which messes up the entire dynamic response prediction from your models. So we built these hybrid models where we adjust the stiffness and damping coefficients out of these TVDs based on experimental data. And much like what we see in the other applications, you bridge that simulation / experimental gap. You close that with these hybrid models without losing the physics. I think that that's the important portion here. Now, everything that you see here, I guess what I shared is public. So we have been publishing and making our publications available. There's links on my web page. For a lot of the applications, there's also GitHub repositories. I guess the list is here, except for few that we didn't get clearance from our collaborators to share. So apologize for that. The credit for everything that you see here should go to these 5 folks here. 2 of them already left the lab. And then there's some that are still around. So this is what I had for today. I think that there's still some time left. So if there's any questions, I would be happy to take them.
That's great, Felipe. Thank you. This is really informative and quite impressive, to be honest. I mean, the amount of engineering work that you have done already using pins. And so, are there any questions? We have time. So, I have a question. So, when you say hybrid, so in my mind, I think that's not what you mean, okay? But in my mind, when I think about hybrid, I think about combining traditional scientific computation with neural networks. Okay, let's say. So machine learning in general. So, but let's say physics-informed machine learning. So combining, let's say, some finite element method, or even ODE solver with physics-informed machine learning. Is that what you mean by hybrid, or?
Yeah. Thanks for the question. So the definition of hybrid here, if I can go back to one of these slides, is what goes into maybe one that is a little simpler. Oh, sorry. Too fast. Yes. The definition of hybrid here is what goes into the nodes of this graph, right? So we are using a data-driven solver, meaning the recurrent neural net is doing the ODE integration per se, right? So now the recurrent neural net is designed as a cell that repeats itself, right?
Mm-hmm.
That cell has elements that are physics informed and then elements that are data driven.
Okay.
And that's why I call them hybrid. For the most part, the known physics is coded in, I guess here I show in blue. The unknown portion of the physics is then carried over by the data-driven portion.
Right.
And then when you present data, what you're adjusting is what you're effectively training is the data-driven portion of the model.
Oh, okay.
Yeah.
Is that related to Bayesian calibration?
It looks a lot like Bayesian calibration. If in the variational application, the variational model, then it's, the formulation is Bayesian. The loss function becomes KL divergence plus the posterior, right?
Right.
So it's fully Bayesian in that sense.
I see. Wow. Yeah, that seems like a very relevant, for real world practical applications,
it's also very enjoyable because as an engineer, you don't feel like you're giving up the knowledge of the physics.
Oh yeah, that's right. That's right. But the calibration aspect is very important. Yeah, absolutely. Yeah, I think it gives a lot of credibility to.
That's right.
To what you're doing. So yeah, that of course that Bayesian calibration paper is quite something we discussed, so yeah, that's really impressive. So are there any questions? Don't be shy, everybody.
Dr. Viana, thanks for coming. This is a really awesome presentation. I was actually curious, you kind of hit on the loss function there for something like here what's on this slide for the hybrid network. And I was actually kind of curious, when you put this together and what are you, how exactly are you minimizing this? You mentioned some KL divergence and some other things that you're, so there's a probability distribution somewhere in that you're minimizing against. Like how are you training this using the RNN-based model?
Yeah, I guess the easiest one to start is, it's something like this. So in this case, for example, we have crack length as a observed variable, right? That you can do just like you're doing recurrent neural nets. You give to the model, you give the input history, and you make predictions of crack length throughout the history, right? Except that you have observations only at few points. Then I guess the implementation gets finicky because you have to do masks and whatnot, but you're minimizing the error between the predicted and the observed crack length at those inspection intervals. Okay. The interesting part to me as a scientist, I should say, is that the observation is done at crack length, but the model that you're calibrating is delta A, is the increment in crack in every step. So for all that you care, you're observing something, but you're calibrating a model of a hidden variable. So it's not straightforward to do that. Well, to see that working is quite simple. So this is pretty simple, straightforward. This is slightly different because now you have two things. First, you have the internal voltage, which you calibrate with a data set that is constant discharge. So you hold current constant and you see the voltage drop. You take the batteries that are pristine out of the factory, and then you adjust that model there. Then you freeze that model, and then you start running these batteries throughout. Once you start running the batteries, you start seeing capacity fade over time. And every dot that you see here is one constant discharge data that you used. And then there's, because that is not measured, it's estimated, you have these uncertainties, right? So you don't want a model that does the whole zigzag thingy there, right? So that's what you don't want. So in a sense, each point here is a point from a distribution, except that the distribution changes over cumulative energy, right? So you do the K divergence there.
I see. Okay, that makes sense.
Yeah.
I should say, Felipe, that Levi is a domain expert in this kind of problems. He's my PhD student, but he's also a fleet commander for the Army.
Okay.
Helicopters for, Black Hawks.
Black Hawks.
And he's a pilot himself.
Yes, yes, sir. Yes, sir. Yeah. We so a few years back, I was working with the Army Research Lab on some predictive maintenance problems, but it was mostly trying to find insights in IVHUM's, health monitoring system data that came out of the UH-60 platform. And so this is way more of an interesting approach for all sorts of reasons. We have the PINS background, and so it's kind of cool to see this rolled in, because at the time it was kind of a rote data driven, let's kind of see where some similarities are, some differences are, and when does this start to fall apart versus this, and this is kind of a more nuanced predictive model that they weren't really able to get to. So no, this is extremely cool work, and I was really excited for this talk. So thanks for coming and doing it. It's really neat.
Well, thanks for the kind words.
Of course.
A lot of this came out of inspiration from, I guess, many years ago. I used to work for General Electric, and I did a lot of work for jet engines back in the day, building models that would predict remaining useful life for different components. And, I wish I had something like this.
Yeah,
right?
Absolutely. Very cool. Very cool.
Thanks.
Yeah, we can talk more offline later, but yeah, so this is something that's right up Levi's alley. I'm sure that he was really looking forward to watching this.
Glad you liked. I think that there was somebody else that had, I guess was Luis, I think.
Yes.
Yes. Hello, Felipe.
Hey,
thanks
Luis.
for the presentation. I am starting actually with physics informer neural networks. So I think it's very interesting, but I am not very good at this time. So my question, I am curious, I don't know, I'm not sure if you have mentioned it. How do you do to know how many data you are using, and first the physics model and data? There is a way or possibility to use more data than the model. I don't know if my question makes sense.
So the question is good. So some of the applications that you see, for example, where people have structural health monitoring, essentially babysitting whichever problem in case. Let's say that you put, an array of sensors that is essentially tracking crack growing for whatever reason, right? And if you have the history of crack length through time, I think that you can do data-driven models, no problem. Like, LSTM or something else, no big deal. You can also do pure physics-based if you want, I suppose. This methodology, I like to think that this has a niche, and the niche is when you have enough to estimate the inputs, and it doesn't need to be the inputs for the model. It could be inputs to the inputs to the model or something, right? So let's say temperatures and pressures are inputs that you need to calculate stresses. You could have temperatures and pressures, but then the stresses get calculated by something else, right? So maybe days or something. So you have enough to be dangerous and estimate inputs, but the output is poorly measured. not because necessarily it's, it could be that you don't have sensors, but it could be that it's not convenient to estimate those or measure those outputs all the time, cost or something else, right? So this is nice because now you don't have much of a chance to do data-driven models because there's this imbalance, right? And then physics would help at least get the models directionally right. And if there is any gap due to aging or due to unknown physics, you could throw that in the back of the data-driven portions of the model, right? Yes. So the student that published this work here, for example, he just sent a paper where he's studying, for example, what's the best way to compensate for this unknown failure mode. We, just as an illustration, we are putting a block in parallel with these other two blocks. So that's one option. But that's only one option. You could put the block, after this one. You could put whatever you want, right? I mean, not clear. So he studied a way for using ensembles of models to average out the predictions and improve the quality of those predictions, right? Now, whether you could use this model to tell you that you need the inspection data or not, right? That would be an interesting way to approach. So if you had the ability to do a variational model, for example, like we did for the battery, right? Yeah. Whenever the uncertainties become too large, that would be a great point to start collecting data again, right? So in this application here, you can see that we come and start clipping the uncertainties here because there's a whole lot of data. And you could argue that maybe, I guess it depends on the application, but maybe by the time that you are around 2.25 kilowatt hour, the uncertainty level is too high, and then you need a new data point there. It could be, right? Okay. So the combination of these models is potentially useful for that as well. We are writing a paper on this battery application that talks about this clipping of uncertainties.
Okay.